So last page of Euler's Complex Numbers, Chapter 16, and the last page of the blue book. Number 3, use the binomial expansion of 1 plus I to the 2n to prove that this left side equals this right side. Okay, so if we take the left side, we can see that this is related to the binomial expansion of this because they have the coefficients from Pascal's triangle, right? So let's look at this and expand it with the binomial expansion because they said that's what the hint is, right? So if we expand this with the binomial expansion, we know that the first coefficient is going to be 2n chooses 0. The second coefficient is going to be 2n chooses 1. Third coefficient is going to be 2n chooses 2. Looks a little bit different than this, doesn't it? And then finally, the last coefficient is going to be 2n chooses 2n, right? And then this is a and this is b. So the first coefficient is going to be multiplied times a to the 2nth power, which would just be 1 to the 2nth power, which is just 1. And so that would be 1 to the 2nth, which is just 1. And it wouldn't be multiplied times b at all because it would be b to the 0. And then the second one would be 1 to the 2n minus 1. And then it would be multiplied times b to the first, so it would be multiplied times I. And then the third one is going to be times 1 to the 2n minus 2. And I, which is the b factor, squared. And I squared is negative 1, so it's going to be negative 1 here. Okay, and the last term is going to be multiplied times 1 to the 0, which would be just 1, and it would be also multiplied times I to the 2nth power, and I squared is negative 1, so it would basically be negative 1 to the nth power, right? Negative 1 to the nth power. So that would be the binomial expansion of this, all right? The other way we could look at it is through Euler's, and so 1 plus I to the 2n is actually square root of 2 times cis pi over 4, right, to the 2n. And if we were going to use Euler's, or if we were going to use de Moivre, we could see that it would be square root of 2 to the 2n times cis 2n pi over 4. And that is equal to, square root of 2 squared is equal to 2, and so that would be 2 to the n, cis n pi over 2. So now we see that this expression is equal to this expression. And this expression can be broken down into 2 to the n cosine n pi over 2 plus I times sine n pi over 2. So you can see that it's got a real part and it's got a imaginary part. And so the real part, which is this, can be equated to the real part of this expansion. And the imaginary part of this, which is this, could be equated to the imaginary part of the expansion. And since we're trying to prove that, do you notice how they removed all the imaginary parts, imaginary terms? So this must be talking about the orange section, and it is. We can see that it is talking about the orange section. So let's take the orange terms and make it equal to the orange term that's left here. So we'll have 2n to the 0, and 1 to the 2 to the nth is just 1. And we'll add that to 2n chooses 2, and 1 to the 2n minus 2 is just 1, so it's just going to be negative, right? Plus dot 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 all the way to 2n chooses 2n, and negative 1 to the n, and that equals the real part of de Moivre's. So that would be 2n cosine n pi over 2. So those two are equal to each other because this is the real part of the binomial expansion, and this is the real part of de Moivre's, so they must be equal to each other. Okay? Number 5. Prove that 1 plus cis theta equals 2 cosine theta over 2 cis theta over 2. Hence, determine that the sum of the series is equal to that expression. Okay, for the proof in number 5, it, according to the book, is easier to start from the right side than the left side. Okay, so if you can prove from the right side going to the left side, then you can just rewrite it as going in the opposite direction also. Now, what you don't want to do is use your proof to like start from the left side and go to the middle and likewise, right? So let's start from the right side, which is 2 cosine theta divided by 2 times cis theta divided by 2, and we'll try to get it to look like that eventually. So first of all, we're going to take 2 cosine theta over 2, and we're going to break down cis 2 theta into cosine theta over 2 plus I sine theta over 2. Once we have this, I think that we could distribute, right? So we'll have 2 cosine squared theta divided by 2 plus I sine theta over 2 cosine theta over 2. And then we could distribute the 2, and I think that can give us a couple of ideas. First of all, if you have 2 sine cosine, doesn't that make you think of an identity? So that's equal to, 2 sine cosine is equal to sine 2 theta, right? So 2 sine theta divided by 2 cosine theta divided by 2 is the same thing as sine of 2 times theta divided by 2, or theta, right? And that's times I. What about 2 cosine squared something? Doesn't that remind you of something too? Remember that cosine 2x is equal to cosine 2 cosine squared x minus 1, right? So isn't 2 cosine squared x equal to cosine 2x plus 1? So let's rewrite this as cosine 2 times theta divided by 2 plus 1. Okay, and now let's rewrite everything. We'll have cosine of theta plus 1 plus I sine theta. Ooh, look at that. I sine theta, cosine theta, isn't that cis theta? 1 plus cis theta. Okay? All right. That was the proof that they asked us to do. They say, hence determine that the sum of the series, hence determine the sum of this series. Okay. When we look at this expression here, doesn't it look like binomial expansion? So it's got the Pascal's triangles coefficient here, and then it's got something there. And couldn't we imagine that maybe if we take the nth exponent of 1 plus cis theta, that we could get something like this? So let's try that. 1 plus cis theta to the nth power. What do we get? So then we'll get Pascal's triangle coefficient, and we'll get 1 to the nth, and we'll get cis theta to the 0, and then we'll get n first, n chooses 1, 1 to the n minus 1, and then we'll get cis theta to the 1. And then n chooses 2, we'll get 1 times n minus 2 times cis theta squared plus dot 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 plus, and the last term would be something like n chooses n, 1 1 to the 0 power, and the last term would be cis theta to the nth power. Okay, let's take a look at this. So basically, we do have Pascal's triangle coefficient each one, right? You can see how the 1 here basically just turns into a bunch of 1s, so it disappears from the binomial expansion. And then finally we have a term which is cis theta to the 0 power, cis theta to the 1 power, cis theta to the 2 power, cis theta to the n power. Remember, using de Moivre's, we know that cis theta to the n power, ooh, that's an ugly cis. Cis theta to the n power is equal to cis n theta. There we go. Look at that. Doesn't that look like that? So that would be cosine of n theta plus I of sine n theta. So this is one of those problems where they're looking at the real part and the imaginary part, I think. Okay, so basically this would turn into r equals 0 to n, and then we would have the cosine of r theta plus I sine r theta. So it looks kind of like that, except for we have an imaginary part too, right? Now let's use the right side and see how we can transform this. So if we know, we took this originally, right? And the right side would be 2 cosine theta divided by 2 times cis theta divided by 2 to the nth power. So let's rewrite that. So we'll have 2 to the nth power times cosine of theta divided by 2 to the nth power, and then we'll have cis theta over 2 to the nth power. So that's going to equal to 2 to the nth power cosine, and we're using, let's see, cosine to the nth power of theta divided by 2, and then using de Moivre's here, it would be cis n theta divided by 2. And if that is equal to this, we could equate the real part and the imaginary part, okay? So let's forget the imaginary part and let's just look at the real part. So the real part would be this would be real, and then we would just use the cosine part of this. Let's try to write that. So we're gonna, on the left side, we're gonna have the real part of the summation. So it'd be r equals 0 to n r, and then it would just be the real part, which would be the purple part, cosine r theta, and I sine r theta, we're gonna ignore that. And we're gonna set that equal to the real part of the right side, which is gonna be 2 to the n cosine n theta divided by 2, and then we're just going to put the cosine n theta over 2 part of this, and we're going to ignore the I sine theta part of it. Is that what we wanted? Maybe it is. I just checked in the back of the book, and that is what we wanted. So that's the end.